Thanks. Okay, so this is work that I've been doing with Michele and Marco from University of Padova and Hongyi Jiang, who's a PhD student at Johns Hopkins. We have been working on these issues for the past almost 2 years now, and I'll try to give a summary of what we've observed. It's a great pleasure to present it at this workshop. Thanks to the organizers for inviting me. Okay, so let me go to the setup directly. So I'm going to talk about these kind of optimization problems, the canonical example being mixed integer optimization. So I have two kinds of constraints. P denotes the convex constraints. So it could be a polyhedron, it could be a closed convex set. And S denotes the non-convexities in the optimization or in the constraints. So most of our results are about the mixed integer lattice, but some of the theorems are applied to more general non-convexities like complementarity constraints, for example. Okay, so at this point, let's just say S is some closed subset of Rn. And we are trying to maximize this linear objective. Okay. So there are two kind of classical algorithms for these problems, cutting planes and branch and bound. And the whole research kind of started when we started wondering about this sort of empirical wisdom, which kind of says that if you just use branch and bound without cutting planes, or if you just use cutting planes without any branching, then they don't really solve very large scale problems. Branch and bound does a little bit better than cutting planes for sure. But even so, when you kind of combine them into what is known as branch and cut, you kind of get a lot more. You can solve a lot more problems and a lot bigger problems. So this is an empirical fact that has been observed for decades. And what we really wanted to do was kind of understand this phenomenon a little bit more mathematically or quantitatively. In particular, we wanted to understand, okay, what kind of cutting plane strategies work with what kind of branching schemes? Is it true that if you just throw together any kind of cutting planes with any kind of branching scheme, you're always going to get something better? Or is it kind of something special? You have to really find appropriate pairs of branching schemes and cutting plane paradigms or strategies. Okay, so that's what we are trying to get towards, kind of build a theory to understand this. Okay, so I'm going to go through some very simple definitions, which is clear to everybody here, I'm sure, but just to set down notation and terminology. So what is a cutting plane? A cutting plane is any linear inequality or half space that is valid for all the feasible points. Okay, and it's non-trivial if you actually cut off something from your convex relaxation. Okay, and a cutting plane algorithm basically iteratively solves your convex relaxation. If it doesn't satisfy your non-convexities, then you add a cutting plane to cut that point off, and you keep repeating. So here's an example, that polygon there, that's our convex relaxation, and I'm interested in the pure integer points in the polygon. And that blue inequality is a cutting plane. For those of you who are in the know, you can see that it's actually a split cut. It's derived from a split disjunction. If you don't know what that means, don't worry about it. I'll explain it later. So you add that cutting plane, you get a tighter convex relaxation, which is this red polygon here. And this is another cutting plane that you can add, and you get a tighter relaxation. Okay, so what's branch and bound? Well, the idea of branch and bound is based on decomposing your initial convex relaxation into smaller convex subproblems. And this is done with the use of what is called a disjunction. Okay, what is a disjunction? It's a union of convex sets, so that together they kind of cover all of your non-convex points. Okay, so a classical example is what are known as split disjunctions. So these are two half spaces where the boundaries are parallel hyperplanes, and together they cover all of the integer points. Okay, so if S is the set of integer points, then split disjunctions are sort of a canonical disjunction family. You could have more general families like crooked crosscuts, T-split disjunctions, many others. And what's a branch and bound algorithm? Well, you start with your initial convex relaxation. You apply your disjunction because the disjunctions cover all of your non-convexities. When you break your initial convex relaxation into the intersections with these terms of the disjunction, you actually don't lose any feasible points. And okay, where does the bounding come from? The bounding comes from the fact that you can actually let go of some of these subproblems if the value there, the convex value, the convex optimization value is worse than some other point that you've already seen, some feasible point that you've seen. Okay, so formally, what I'd like to do is keep track of this branch and bound algorithm using what is known as a branch and bound tree. I'm sure all of you know what a branch and bound tree is. Essentially, you start with your initial relaxation. I'm sorry, my slides are not really. Okay, this is much better. So if it's in full screen mode, my slides are moving very, very slowly. So I'll just switch away from the full screen mode. Okay, so yeah, so I was talking about the branch and bound tree. Essentially, you keep track of these sub-problems you're creating in the form of a tree. The root is your initial convex relaxation. Every time you apply a disjunction, you create children of your current node that you processed. And the idea is that when a certain node falls below a bound of your objective, then you kind of forget about that node. So that node becomes a leaf node. That's what is pruning. And you only process nodes that are still above the bound that you're trying to reach. Okay. So if the bound you're trying to reach is just optimality, then you would of course go all the way to optimality. Otherwise, you can stop at any kind of upper bound that you set yourself. Okay. Okay, so this is all just well-known terminology. I just want to point out that although we think of disjunctions as applied to branch and bound and branching schemes, you can actually use disjunctions for deriving cutting planes as well. And in fact, technically every cutting plane is derived from some disjunction. So how do you do this? Well, you just think about the intersection of your disjunction with your initial convex relaxation. And any half space that is valid for all of these subproblems is a valid cutting plane, because of course the disjunction was covering all of your non-convexities. Okay, so that's how many of the cutting planes are actually technically every cutting plane that we know of is derived in this way from some disjunction. Okay, but this is going to be important in the setup that I have. So for example, here, like I said, there are these canonical disjunctions called split disjunctions, which are two-term disjunctions. And this blue line here is valid for the intersection of the original convex relaxation with the two sides, the two half spaces that I have in the split disjunction. And therefore, this is a cut that is derived from this disjunction, and such cuts are called split cuts. Okay. Okay. And what's a branch and cut algorithm? Well, it's just a modification of branch and bound, where at every stage, when you're deciding whether, okay, here's a subproblem that I want to process, you can add in a new step here, which you see in step 2b, where you decide whether you want to add some cutting planes locally to this subproblem, or you want to branch on this based on some disjunction that you choose. Okay, so that's branch and cut. Okay, good. So how am I going to really talk about efficiency in a rigorous way? Well, what I'm going to focus on is that the main computational overhead in any of these algorithms is really the intermediate linear or convex optimization problems you're solving. Okay, I'm kind of ignoring the time it takes to generate cutting planes or choose a disjunction. That's an important aspect of the computations, but in my opinion, just firstly, to keep things mathematically clean, and secondly, also, I think the major computational overheads are really these optimization problems that you solve at every stage, compared to the time you need to spend to generate cuts or generate disjunctions. Okay. Of course, one can debate this, but that's going to be my setup. So I'm going to focus on two aspects of this. So firstly, how many LPs or convex problems do I solve? That's sort of the first order of complexity. And also, how difficult are these LPs and convex optimization problems? So the second thing is a little bit harder to formalize. And we are really going to focus on a very concrete measure, which is the sparsity of constraints. So if you're talking about nonlinear constraints, what do you mean by sparsity? So let's just think about linear constraints that you add when you apply these disjunctions or you add cutting planes. And we are going to say that a problem is more complicated if the constraints you have in that problem are dense as opposed to being sparse. Okay. All right. So with that setup, I'm going to start diving into the results we have. So I'm going to first focus on just the number of linear programs or convex optimizations. I'm going to forget about sparsity for a second. And in the second part of this talk, if I have time, I'll tell you what results we have when we introduce sparsity also into the mix. Okay. So the first thing that we wanted to understand was, when does cutting plane or branch and bound dominate the other strategy? So are there settings where, for these problems, you can just use a cutting plane algorithm? There's no point in doing branching. And for these kind of problems, branching is always good. Once we understand that, in what situations one strategy dominates the other idea, then we can try to figure out when it makes sense to combine them to get some advantage. Okay. So the first set of results is comparing cutting planes with branch and bound. So pure cutting plane algorithms and pure branch and bound algorithms. And just to make the playing field kind of even for both, I am going to say that I'm going to fix on a family of disjunctions. And the branch and bound algorithm I consider is going to be based on that family, as well as the cutting planes that I derive are going to be derived from that same disjunction family. So in this way, I'm really focusing on the sort of mechanics of the algorithms themselves, as opposed to giving them sort of different amounts of information, right? So if both of them are based on the same disjunction family, then somehow the information they have is the same. And now we can really try to figure out what's really different in the algorithms themselves. Okay. So in this table, I focused on two families of disjunctions. One is what are called as variable disjunctions. So think about any integer variable, and the disjunction is that this integer variable is less than equal to some integer k, or greater than equal to that integer k plus 1. Okay, so that's a variable disjunction. And you can choose any integer variable you want. You can choose any integer k that you want to sort of apply this disjunction on. That's the family of disjunctions I'm going to consider. And I'm going to look at cutting planes as well as branch and bound based on this family. And the second set of disjunctions that I'm going to look at are general split disjunctions, which is what I said earlier. So you have two parallel hyperplanes, so that the two half spaces that you have from them cover all of your integer points. Okay, and so cutting planes derived from this are going to be split cuts. So I'm really going to be comparing a cutting plane algorithm based on splits versus a branch and bound algorithm based on general splits. Okay, so those are the four columns. Why four? Well, I'm also gonna distinguish between 0-1 sets and general convex sets, right? So 0-1 problems are where the convex set is a subset of the 0-1 hypercube, and I'm really interested in the 0-1 points. And general convex sets is going to be just general convex sets with general kind of non-convexities, but let's just think about integer points for now. The two rows correspond to whether the dimension of the problem, the number of variables you have, is part of the input or not. So your complexity measures can depend on the dimension in an exponential way, in a polynomial way. In the first row, I'm allowing the dimension to be part of the input, so I can speak about being exponential or polynomial in the dimension. And in the second row, the results are about fixed dimension. Okay, so it's a constant, and the results are in that setting. Okay, so the first result, just let me try to interpret this table. When I say CP less than equal to BB, that's highlighted in blue. What that means is that if you look at cutting planes based on variable disjunctions, which in this setting, in the 0-1 setting, correspond to lift and project cuts, and you look at a branch and bound scheme based on variable disjunctions, then this theorem says that cutting planes always do better than branch and bound. Particular, here's the theorem. So if you have a branch and bound proof or a branch and bound algorithm, this should have been an algorithm. I haven't introduced what proof is. So just think of this. If there exists a branch and bound algorithm that produces k nodes in the tree, then you can sort of prove the same inequality, the validity of the same inequality, using a cutting plane proof of the same size if you allow a little bit of slack. What's interesting is that the size of the cutting plane proof actually doesn't depend on epsilon at all. So for every epsilon, you get the same cutting plane proof size, but we are not able to prove it for epsilon equal to 0 in the general closed convex set. It is known that if you're in the linear case, in the linear setting, then actually the theorem holds with epsilon equal to 0. And this was a theorem by Sanjeev Das from quite a while ago. So the main thing that we do here is actually generalize it to the nonlinear convex setting. Okay. So in this sense, I mean that cutting planes are always as good as branch and bound. Okay. There's always a cutting plane algorithm that does at least as well as the branch and bound without compromising on the number of optimization problems you solve. What was not known is whether cutting planes can be strictly better than branch and bound. So we actually came up with a family of stable set instances where these cutting planes, these lift and project cuts, can solve the problem in polynomial time, polynomial in the size of the graph, whereas any branch and bound algorithm based on variable disjunctions is going to take exponential time. Okay. So it shows that while cutting planes can always do at least as well as branch and bound, on certain instances like stable set instances, you can actually be much better using lift and project cuts. Okay, so the example is actually, there are many examples. This is I think the simplest example we came up with. It's a stable set on a disjoint union of triangles, n triangles. It's easy to see that you can actually convexify each of these individual polytopes with cutting planes. So there's a cutting plane algorithm of complexity n, and you can also show with some analysis that any branch and bound tree that solves this problem has size at least 2 to the n. Okay. When we move over to the general convex setting, so away from 0-1 problems, then actually this advantage of cutting planes disappears. There are now also examples now you can create where branch and bound finishes in constant time, whereas any cutting plane algorithm based on variable disjunctions will take infinite amount of time to converge to the value. If you are happy with epsilon approximations, then it converges in polynomial in 1 over log 1 over epsilon time. But nevertheless, it's constant versus polynomial or constant versus infinity, depending on what perspective you take. Okay. When you move over to split disjunctions, the story completely changes. Somehow the branching scheme now gets a lot more power, and the extra power that you get with split cuts doesn't really compare that well. What do I mean? Again, there's a theorem we have which says that if you look at general splits, if you have any cutting plane algorithm that solves the problem with k cutting planes, then there is also a branch and bound algorithm that will solve the problem with at most a blow up of size 3. So the entire branch and bound tree will have at most 3 times as many nodes as the cutting planes, as the number of cutting planes you used in your cutting plane algorithm. Okay. So somehow when you use general split disjunctions for your branching, you can always dominate split cuts up to this constant factor. Okay. What we do not know, and what is an open question so far, is whether this can be made strict, right? So are there instances where branching on general splits can solve a problem in polynomial time, whereas split cuts take exponential time? We don't know of an example in the 0-1 setting or in the general convex setting. So this would be a nice problem to sort of resolve. We haven't been able to do it so far. Okay. It turns out that when you go to the fixed dimension setting, then again, branch and bound seems to be doing better than cutting planes. The precise theorem is the following. And of course, in fixed dimension, the 0-1 setting is kind of trivial because there are only finite sort of constant number of feasible 0-1 points that you have to enumerate, and you can show that it's easy to do with branch and bound or cutting planes. So the really interesting case is the non-0-1 case, the general convex setting. Here, the setting is the theorem, precise theorem we have is the following, that if the disjunction family is kind of controlled, meaning that the number of inequalities you need to describe your entire disjunction is bounded. So that's what I mean by the size of a disjunction and the size of a disjunction family. then, so suppose the size is bounded by m. So for example, for split disjunctions, the size is bounded by 2 because I need 2 inequalities to describe any disjunction in this family. But in general, okay, so you have m, and this is a theorem which applies to more general non-convexities. So S is not necessarily just a mixed integer lattice, it can be a general non-convexity. Here, what we can show is that if you have a cutting plane algorithm that solves the problem in time k, and there's also a branch and bound algorithm that is whose tree size is at most a polynomial blow up, assuming the dimension is a constant, right? So you see the dimension here appearing in the exponent. So if it's a constant, then this is just a polynomial blow up compared to your cutting plane algorithm. So that's what we really mean here when we say that branch and bound is less than equal to cutting planes. What I mean is up to this polynomial blow up. And you can also create examples where if you fix on the variable disjunction family, the gap is actually constant versus exponential. So branch and bound can be much, much better. If you go to more general split disjunctions, then the gap becomes constant versus polynomial. We have not been able to establish constant versus exponential. In fact, this is another big open question that I'm happy to talk about after the talk. Okay, I see that I'm running out of time and I have only 2 more minutes left. So let me just talk about, okay, so far we have been trying to understand branch and bound versus cutting planes. And the intuition is that, okay, if there are these settings where the branch and bound algorithm is always going to do better than cutting planes, it probably doesn't make sense to add cuts also into the mix because you can do whatever you were doing with just branch and bound. Or if cutting planes is always better than branch and bound, then again, you probably are not going to see much of an advantage, at least mathematically, when you combine them into branch and cut. So that motivated us to define this notion of when a cutting plane strategy and a branching scheme are doing different things. So we say that a cutting plane paradigm or strategy and a branching scheme are complementary if there is a family of instances where the cutting planes are polytime and branch and bound on this branching scheme is exponential, and vice versa, there's no domination. So there's another family of instances where cutting planes take exponential time and branch and bound is polynomial. And the theorem is very simple, that if you have a complementary pair of branching scheme and cutting planes under certain regularity conditions, which are satisfied for all branching schemes and cutting planes that I know of, so they're pretty mild, then you can show that there is a family of instances where branch and cut has polynomial size proofs, or it finishes in a polynomial time. But any branch and bound algorithm will take exponential time, and any cutting plane algorithm will take exponential time on this family of instances. So this rigorously shows that branch and cut can be exponentially better than branch and bound alone or cutting planes alone. Okay, so I'm officially out of time. Let me just say that this definition of being complementary is not an empty definition we have made. It applies to, for example, the quartal-Gomerich paradigm of cutting planes and the family of variable disjunctions for branching. So if you branch only on variables and you use quartal-Gomerich cutting planes, then combining them is a good idea according to this theorem. Okay. And of course, you can apply this to other kind of families of cutting planes and branching schemes and figure out whether they are complementary or not. Okay, so we have focused on the number of LPs. Of course, I also wanted to say something about sparsity, but I am out of time. So I'll let the hosts decide whether they'll let me take 2 more minutes or whether I should just stop here.
Yeah, please go ahead and explain. Like you have 3 minutes.
Okay, I'll take a couple of more minutes. So here's a classic example that kind of shows that sparsity makes a big difference. So this is an example that Jaroslaw first came up with. It's a 0-1 problem where you say that twice the sum of the variables has to be equal to an odd integer. So of course, there are no feasible integer points in this. And he showed that any branch and bound proof of infeasibility is exponential. This is one of the first examples where branch and bound was shown to be exponential rigorously. Okay, but these were branches based on variable disjunctions. of course, if you allow more general split disjunctions, then there's one single disjunction is going to solve this problem and show you infeasibility. So clearly, if you allow your disjunctions to have only sparsity 1, so only one of the coefficients can be non-zero in your disjunctions, then the branch bound proof is algorithm is exponential. Whereas if you have unrestricted sparsity, if you allow all coefficients to be non-zero, then you get constant size proofs. So we asked, okay, what is the trade-off? Where does it really change from constant to exponential? And we have this theorem that, okay, actually, even if you go all the way to n/2 sparsity, you will basically have exponential as long as k is essentially a constant. We have other lower bounds in our paper, which kind of show even if you go all the way to n/2, you still get square root of n as a lower bound on your branch and bound algorithm. But anyway, so we kind of show this smooth transition as you kind of tweak the sparsity parameter, what happens to your branch and bound tree. What is the trade-off? Okay, so let me just skip all of this. And there are some questions, like I said, it would be nice to sort of, understand the role of sparsity a lot more. We have some initial results, but I think there's a lot more to be done. Showing the converse of our theorem. So we gave a sufficient condition where branch and cut is exponentially better. It would be nice to show that that's actually a necessary condition, that whenever branch and cut is actually doing better, the branching scheme and the cutting plane paradigm are sort of complementary. They are doing two different kinds of things. That would be nice to show. This was an open question, like I said, show that branch and bound based on splits is strictly better or exponentially better than split cuts. And let me just stop there.